All right. We are continuing on with our crawl through understanding texture to understand visual understanding. So we last time we talked about various ways of capturing some of the information that we know the visual cortex is processing. These filters that compute various oriented derivatives. How can we try to use that same processing to get towards understanding, modeling the visual world? And we talked about some ways to compute statistics of these measurements. Okay? And we talked about the first super simple idea was to just compute the means of these oriented filters. And we saw that even just computing the means of a whole bunch of filters, right? So that's like, you know, if you have 7 filters, it's like 7 numbers per image. Even using these 7 numbers, you know, you plug them into your, you know, classifier like SVM or whatever, and you can already do surprisingly good job at recognizing images with different textures. Now, this is still not quite, you know, what we wanted to do is to see if we can recognize, you know, say pictures with animals versus pictures without animals. The Thorpe study that we showed that humans could do, humans and apes. But this can already, just the simplest thing here, can already surprisingly well recognize different types of texture. Okay, textures that you haven't seen before, right? So you compute this on training set of textures, just like your standard machine learning setup. Training set of textures, you compute this, and then on test set, you can actually do something. Okay? Then our idea 2 was to say, instead of computing just one number per filter, like the mean, what if we use some higher order statistics? You can say, okay, mean plus variance, you know, standard deviation, whatever, kurtosis, or you can just say, okay, I can just get a histogram of values. So for every oriented filter, I can compute a histogram. And we talked about kind of computing histograms of all the filter response images. And then we showed that that information is enough to synthesize, given a texture, to synthesize novel texture that has the same distribution but is completely different from this texture, this problem of texture synthesis. So that means that these are sufficient statistics for capturing enough of the information that you can actually create novel imagery. And we show that this works okay for kind of more stochastic textures. Doesn't work as well on the more structured textures. And then for that, the idea was to go back to Ulish and say, what about taking not just the first order statistic, just the histogram of each filter separately, but look at pairs of filters and compute statistics of pairs. And once you do that, then you can get even more powerful representation, and you're able to capture more structured texture. So it's a representation that captures the essence of texture, but it doesn't need to be exact same texture. So this is kind of a towards the idea of generalization, right? Where you're capturing statistics, and then you're seeing other examples of that texture, and those statistics are able to recognize it for you. Okay? So there is more. If you push more along the direction of having different filters talk to each other, not just maybe pair second order statistics, but seeing how all the filters together jointly represent something, we get into something a little bit more general, and this has sometimes been called the computational version of textons. Again, Yulish is weighs heavily on all of this research. So Yulish had his textons that he created, this ephemeral elements, textural elements that he never really defined what they are for real images. And so the idea here is to see if we can operationalize the idea of visual text of textons. They're also sometimes called visual words. And the reason they're called visual words is by analogy to the bag of words representation in text. Hopefully, everybody here has taken 189, so you know of the bag of words. Anyone can define bag of words for me? What's a bag of words representation in text? You did a whole bunch of assignments on that in 189, presumably. Yeah?
Like we take all the words and we do a vector with 1 over 0 if the words exist, like for example in the sentence or not.
Just 1 or 0?
Yeah.
What if there is this word occurs twice?
It's more of a count of like words.
What do we call a count?
Frequency.
In other words? Huh? It's a histogram. It's a histogram of words, right? Every word you have a count how many times that word happened, right? That's what a bag of words is. It's a histogram computed on the list of all the words in the world, in the dictionary, right? And that turns out that histogram of words is a very good representation for a particular document, right? So you look at that bag of words and you can see if it says some medical terms, and you say, okay, this is a medical document. If it has legal terms, it's a legal document. It has Trump and Clinton, that it's a political document, right? So, and the nice thing is, of course, those histograms are fixed length, right? If you have documents, if you compare documents to each other, like you cannot do L2 norm, for example. You cannot do it, because they're different lengths. They don't live in the same vector space. But the histograms, they're all fixed to be the same length. So you can do computing on those histograms. So bag of words has been very, very powerful in text representation. And here the idea is to do the same kind of thing, except the histogram is going to be over what we call visual words, right? So this says analogy to documents. You look at a document, you look at the histogram, it says, oh, sensory, brain, visual perception versus China trade, whatever, right? And those are the descriptors. Those are the sufficient statistics that separate that they can use to classify different documents. Remember when you did in 189, you're writing some classifier that specifies spam versus non-spam email, right? The feature you used was the bag of words feature. You histogram all the words in the email, and then you train a classifier that says, okay, if it has these, get rich quick kind of words, then it means it's more likely to be spam, and if it doesn't, it's more likely not to be spam, right? So the same thing, you can think of this being kind of like a texture representation, right? The words of the document, the sentences, the patterns, they will be different, right? I write a different, trade document. It will not be exactly the same as this one. But chances are the descriptor, in this case the bag of words histogram, is going to be very similar. So that's our invariant. That's our feature that we use in text to represent text texture. Okay? Everyone clear on this? Questions? So the same thing we want to do for visual imagery, right? We somehow define pieces of the visual world to be what they call visual words. And in the same way as with text, you can compute histograms of each image as a histogram of the different pieces, the different visual words. I have You know, in this one, I have that much of the cheek, I have that much more of the eye, but they have very little of the bicycle seat, right? Classic standard histogram story, okay? But now here, the idea is that we're doing it on this kind of more higher level image patches, right? Not just histogram of orientations, but something more semantic. The only problem, of course, is we don't know how to get there. So in text, well, word is a word. You know, you say the word China, and it's basically, you know, there you have this occurring, you know, tens of millions of times. That's the identifier. That's the symbol. You just count how many times the word China occurs, and that you put it in your histogram. In the visual world, every 5 by 5 or 10 by 10 patch of pixels, it will almost never repeat, right? There is enough variety in the visual world that, and any 10 by 10, there are more 10 by 10 patches of pixels than there are atoms in the universe, right? It's a huge number. So you're almost never going to have two patches with exactly the same pixels. So that's the big difference between text words and visual words, right? In visual words, you somehow need to collapse the representations into something that resembles words that you can then find them again and again, so you can histogram. Because you don't want to have histogram with only once, right? Only everything occurs just once, right? That will be the case if you just count the unique occurrence of patches. So how can we go from gazillions of unique patches to something like a dictionary of visual words, to make it more like textual words? Classification? How?
First define some types of objects and then classify.
But the problem here is that we're not doing it on objects. We want to do it on these kind of basic types, like the words, not the full documents. An object here would be a document. Here we want to like a low-level piece of that document. So we don't actually know what they are. So we can't, we cannot label the ground truth because we don't know.
So it may not be an answer to your question, but more like a question.
Uh-huh.
Is in the case of images, we have an extra signal, which is the intensity signal that we have been dealing with over the past few lectures.
Well, that's the only signal, really. That's not the extra signal. That's the only signal we have.
But so in words, yes, I agree that each word is uniquely defined. So in visual information, why don't we use that signal instead?
No, we can. But what I'm saying is that if we just look, let's say we take a patch of 10 by 10 pixels, right? 10 squared pixels. How many unique patches are there like that? How many? Huh? 256 values per pixel. Let's not worry about color. So 256 per pixel, and then
Power 100.
Power 100. That's a huge number. It's a humongous number. So it's a huge space. And in that space, yes, the patches are not represented uniformly in that space, of course. But even so, the chance that you'll have any collision, that you have two patches that just happen to have exactly the same representation, are minuscule. In text, you have the word China, and then again you see the word China. Look at this. It's again the same thing. I'm going to add 2 to the count, right? That just will not happen in vision. So we need to have some extra step. Some extra step to make patches that are kind of almost close to each other. We're going to say, okay, we're going to assume that they're going to be the same. We're going to count them as being the same.
We could use order statistics or the 8 filters that we showed, and then use that the 8 value vector as a characteristic of each.
You can do that, but it turns out that even then, because those values, 8 values, they're actually real numbers. They are not integers. So even then, you will never have exact matching. They're all going to be slightly different. So again, you're not going to get them to match. So again, like for computing histograms, you need to somehow get things that go into the same bin. So you can bin them, and we have seen how we bin them. But here we want to somehow capture bin for all of those 8 patches, all of those 8 values, for example. You have studied the answer to this question in 189. What do you do if you have a huge amount of data and you want to represent the data with a dictionary of, say, 100 things? How do you construct a dictionary? PCA cluster, okay. I mean, PCA is type of clustering. What are other type of clustering? PCA maybe is a little bit too complicated for me. Huh? That's not a clustering algorithm. K? K? No? K? Means. You guys. Ah. Already one semester and everybody forgot everything. K means vector quantization. That's a clustering algorithm to take from a huge amount of little tiny instances and collapse them into a dictionary of elements. So that's exactly what we're going to do to collapse all of our. We're going to take patches from our image. We're going to represent them somehow. I don't really even care. You can take pixels, but of course we like to be like V1, so we're going to take the filter vectors, like those 8 vectors or the 30 vectors, whatever. But that doesn't matter really. So we have a feature representation that represents each patch. So for every pixel we have that thing. And then they're going to be somewhere in this 8-dimensional or 30-dimensional feature space. And they're all going to be very different. And so what we're going to do is we're going to cluster them into visual words using k-means, vector quantization. Vector quantization is k-means. That's the algorithm that was, that was designed to do this kind of clustering for you. Okay? And now you have cluster 1, cluster 2, cluster 3. Those are your visual words. You have word 1, word 2, word 3. Now we can finally do histogramming. Now you can count. Okay? So here's one way to do this. We take our filter bank. This is like a 50-dimensional filter, 50 filters, so like 50-dimensional, right? So you apply your 50 filters to your image. So at every pixel now, you have this vector, okay, 38, whatever, 38-dimensional vector of the dot products of the filters with the patches, right? So that's your filter representation. And now you say, okay, now I want to take that representation, I want to cluster it. Okay? So here's one example of what happens when you cluster. So here is an input image, and here is a bunch of these clusters. When you cluster those filters, and now here we can reproject them back into image space to see what those clusters actually look like, because you can, again, use inversion to invert and see what the thing look like. And you see a whole bunch of clusters that are dots. And we can also represent those clusters by putting 1 when the cluster is a particular, when this cluster shows up, when this cluster shows up, when this cluster shows up, etc. And so you can see that it kind of gives you a representation of however many, it's 5 by 5, 25 visual words representing this image. Okay? Here is a different image, and you can see kind of different clustering here. Okay? And the representations here are also called text tones, visual words, key points. They're k-mean clusters pieces of the image. And again, people have used various different ways of what you cluster. The filter bank responses are kind of the more biologically inspiring, and those usually called textons, to pay homage to Ulish. You can just take raw pixel patches, just 5 by 5 patch, so 25 pixels, and just cluster those. That works not as good, but you can still do it. Or you can use some sort of other descriptors. For example, maybe some of you have heard of sieve descriptors. That's another way to describe a patch. You can cluster those things as well. You can cluster it per image, but more usual is to do a universal dictionary. So you take a whole bunch of images together, like 100,000 images, and you do clustering on all of those 100,000, and you get these dictionary of universal visual words, and then you apply them to everything you want. Okay, and that captures the co-occurrence statistics between the different pixels or different features. Okay, so here is one kind of an universal representation. These are your textons, code words, and this is how often they occur here. So you can see that they kind of looks like visual, kind of a visual analog of bag of words. Except, of course, these guys don't quite look like that beautiful picture. There is no like wheels and noses and cheeks and stuff, right? These things are much harder to understand what they are, but otherwise, this is kind of the same story, right? And so, of course, once then you can use whatever algorithm you want for actually computing with this. So again, to learn this representation, you compute your dictionary with k-means, right? And then you have every image now is represented by this bag of visual words, okay? And then at test time, you have a new image. How do you do recognition with a new image? If you want to recognize what was on that image, what do you do? I mean, there are many ways of doing, but give me like the simplest thing to do.
Computer code work, and then compare it with the frequency of the thing that we got before. And
Yeah. Well, this is called K.
K-means.
No. Now the other one. K nearest neighbors, right? You compute a representation, and then you compare that representation with all the other images that you have seen, and then you see which one matches the best, right? That's your classic, your dumbest machine learning algorithm. We'll chat. We'll refresh you about that later. But right, you just find the nearest one. You can do other things as well. You can do some sort of a linear discriminant, whatever. But the simplest thing is you take this for a new image. You have your bag of words, and you compare it with the bags of words of other things you have seen. Or you can you can train a classifier SVM, whatever you want. Okay. So now we're ready to revisit this amazing and magical Thorpe study, where humans were able to tell images with animals versus images with non-animals. Okay, this is not exactly the study. I think Thorpe also did this study as well. This is maybe a little bit more fun, because here what you're trying to do is you have instead of 2 classes, you have 6, 7, 8, 9, 10 classes, right, of different images. And the images are beach, mountain, forest, city, street, farm, kitchen, living room, bedroom, bathroom. Okay? So you're presenting people with one of these 10 images, and then the person is supposed to tell you which class it is. And the person is supposed to do it very, very fast. So this, again, pre-attentive. So you're trying to see pre-attentive human response. Okay? And now we want to see if we can have a computer try to do the same thing. Okay? And what we're going to do is we're going to do the simplest thing. We are going to do this text-on histogram visual word type representation. Okay? So what we're going to do is we are going to take all the images that in our training set, we are going to compute a universal code book, a histogram of these visual words. And then for every image, for every new image, you're going to use that code book to compute a histogram for that image. So here is your universal text tones. There is maybe like 300 of them. Okay? And then you're going to compare that histogram to all the histograms of all the data set that you have already in your training set. All the images with labels, right? So you have in your training set, you have, okay, this image and it says label bathroom. This label beach, right? And then you compare this new histogram to all the histograms you have seen before. You pick the closest histogram. So this is not even k nearest neighbor. This is 1 nearest neighbor. Even simpler. The closest one, the closest histogram, and you just steal that label. And you say, okay, this image is probably going to have that label. Clear enough? Yep.
How do you have the height of the, like in the histogram of every patch?
The heights?
Yes, the height. It's the number of occurrence.
The number of occurrence. It's a histogram, exactly.
But
So,
exactly. Do we have exactly the same, like the same image? Like when we say, for example, there's three times the first patch. Is it exactly the same, or like we take the nearest?
Remember that what this is. This is a k-means clusters, right? So you have every new patch is going to be, you are going to take every new patch. That's not going to be like anything we have seen before, but we can then go and project it onto the keyword in the keyword dictionary, and we can see where it lands among those 100 text tones. Where is it closest to, right? This is where this is what vector quantization is. Vector quantization is you have a new vector and you want to quantize it into one of 100 things. So you're going to, at test time, for every new patch here, you're going to see which one of those 100 is closest to, and then you're going to just assign that number to that, right? So that's the vector quantization at runtime. And once you assign a number, then it's easy because now you have 100 bins and you just add one to what the appropriate bin. That's exactly why we need to use k-means. That's why we need to use this vector quantization, so that we can go from the insanely huge number of possible patches to the 100 patches that we're just going to project everything down to. Okay? Is that clear? Yep.
Is this algorithm any sensitive to the size of the patch? Because it seems like if you are working with different categories, the size of the patch might matter to classify that.
Fair enough, fair enough. So what, if you remember for the filter banks that we had, they actually had filters that were small and medium and large. So there was actually many different filters. So theoretically, you might have some things that respond to bigger filters, some things that respond to smaller filters. But it's true that when you're clustering them all together, it might still not be very sensitive to variations of scale, for example. So something that's very close versus very far away. So people thought this would be a huge, huge problem, and then people were thinking, okay, I'm gonna do this at multiple scales, or I'm gonna do small ones a bit. Turns out, doesn't really matter that much. People worried about it for a very long time, and then they turned off all of that, and it still basically worked the same. It's amazing how robust this stupid thing is. Okay? So everybody's clear on this. So the only last thing is, how do you do nearest neighbors? What distance do you use for nearest neighbors here? Because these are now nearest neighbors between histograms. How do you compare distances in histogram space? What kind of statistics?
Mean, variance?
Okay, you can fit like a Gaussian to it, and then you can compute, then it's kind of mean variance kurtosis. That's one way, but I don't want, if you're fitting a Gaussian, that doesn't look Gaussian at all. So if you fit a Gaussian, you're going to lose a lot of information. Yeah?
Maybe you do the square error. You do the difference of the two.
So the square error is not actually a very stupid statistic. It's okay. It's not the best, but it's actually, you know, it's not bad. It turns out if you go to your statistics textbook, there is a bunch of metrics for comparing distribution, comparing histograms. One of them is the chi-square test. You can look it up what it is, but it's not that different from mean squared error. But yeah, there's various ways of actually comparing histograms. Chi-square is a classic one. So now we are ready to roll, okay? So now, here is the results of our super dumb texture model. These are our 10 classes, and these are the percent correct, okay? So this is a 10 class classifier, right? So 10 is going to be our chance level. So we're not doing amazing, but, you know, we're doing okay. We're doing, you know, particularly good for, you know, forests and living rooms, okay? But actually the reason we want to do this is we want to compare this with human performance. And again, remember, this is a harder task than just animal versus humans, animal versus non-animal, because this is 10 classes. So in animal versus non-animal, your chance is 50%, right? Here your chance is 10%. So everything's going to be lower. Okay, so now let's see what humans do. I was actually participating in this study, so this is chance. So if humans are given only 37 milliseconds, super short time, this is the result of how they do. If humans are given 50 milliseconds, this is how they do. And if they're given 69 milliseconds, this is how they do. Okay? So for very short pre-attentive amounts of time, it looks like our model captures more or less the same information as humans. So for very quick judgments, when it just hits the, the visual cortex, you don't give it that much time at all. It seems like our very stupid, let's look at the statistics of patches of our image, is actually doing surprisingly similar to what humans do. Now, this is, of course, not saying that this is exactly what humans do, but it's an indication that something very dumb and simple can actually account for quite a bit of the human performance at this very fast pre-attentive regimes. Okay? Any questions on this? Right? It's kind of interesting, right? Because basically what it says is that there's some low-level statistics about a forest versus a living room. It's not going to find you chairs in the living room. It's not going to find the table. It's not going to find the TV, right? There's no capacity in the model to do any of that. It's just looking at statistics of stupid, tiny little 5x5 patches. But it's still able to do something. What do you think it is? What do you think allows it to do well on something like forest? Yeah?
Maybe the texture is almost the same in all the image. And
So what kind of texture? What do you think is the kind of this?
vertical.
Exactly. In a forest, there's probably lots of vertical things and not that many horizontal things, right? It might be as simple as that. It's really doesn't have to be that super difficult, right? It could be that in a forest you have a whole bunch of vertical stuff. In a living room you have a whole bunch of horizontal stuff. It's texture. So you would think that, when Stella was talking about texture, you would think, okay, texture is like, you have sand on the beach, or you have yogurt, or you have, plate of rice or something very, very repetitive. Here we're talking about things that are naturally not really, there's some structure in the image, not just texture. But it turns out that just treating it as simply as texture is maybe good enough, at least to do something. So I'll show you another example of this. This is what in computer vision we call object recognition. And that's a total big lie. In fact, most of the things, even what we're doing right now with ImageNet and all that stuff, we call it object recognition. Don't believe it. It's texture recognition. Has nothing to do with objects. It's just looking at these stupid local statistics, and I'll show you. This is an old paper, but it's oldie but goodie because of how well it works. So this is a task of recognizing objects in a data set. There's, I think, 20 different objects. Here's the kind of natural data. This is out of Cambridge. It's a Microsoft Cambridge data set. And the idea is they're going to compute textons for the images, and they're going to do exactly the same thing as we did with that experiment with living rooms. They're not going to do nearest neighbor because they want to be real time, so they compute a very simple classifier, but I think it's just a linear classifier to classify between those 20 different objects. And here's their video. So what they're doing is they're getting a little thing, computing textons really fast, and then just doing a linear classifier to figure the nearest one of the which one of the 20 classes. So you look and say, wow, it's working. Vision is solved. It's done. Look at this. Magic. Look at that. Look at this. Oh, bicycle. Another bicycle. Another bicycle. Now what they don't show you is if you just do that, it still says bike. Because what is it doing? What is it doing here? For the bicycles. It's just looking at this pokey texture. That's all it's doing, right? The same thing, but texture can get you so far. Look at this. Any piece of a car, even like the little point of a car, it says car, right? Look at this. 3 cars, it says car. Tree, car, car. I mean, look at this. Vision is solved. Look at that. It's, I think, a very dramatic visualization of not how smart computer vision algorithms are, but how much you can do with very low-level stuff. With very low-level statistics, you can do so much more already. And we often forget about this. We often ascribe to our methods the amount of performance that they don't possess. Okay, so whenever you're doing some computer vision project, you should always keep this in mind. That on one hand, on the good side, you can do a lot with stupid low-level statistics of image patches. But on the other hand, you're still in the end doing stupid statistics of image patches. Okay? Should not forget this. Any questions about this? Yeah?
Just curious about the performance of this approach. Like,
yeah, it was very good. It was very good. I mean, this is like 2003 or 4. So it's not as good as the current methods, of course. But it's not like, it's pretty good. It's pretty good. And I would argue that the current methods, and I will show you some example of that, the current methods, even the ones using CNNs, they're not fundamentally much different from this. Because what we can do is we can take an image and we can scramble the image around, preserving its statistics. And the classifier is just not going to care.
and then follow-up is like, what are the likely failure cases for an approach like that, where we are just classifying based on the...
Oh, no, but we've already seen this, right? It says bike even if you're showing like a quarter of the bicycle, right? Because it cannot separate the instances. It cannot tell you one bike from the other. It cannot tell you one car from the other, because all it's doing is say, oh, there's some bike texture, right? Bikes are particularly easy. So if you see bikes in recognition paper, be careful. Because bikes have these spokes. So remember we have all of these filters, oriented filters. So the spokes are perfect because like every single filter is happy, right? So it's a very nice signature. So yeah, bicycle wheels, even car wheels, very easy, okay? So yeah, so one thing that this thing cannot do is it cannot separate instances. And we will talk about this later in the course. Once you want instances, suddenly things become much, much harder. Any other questions? Okay, let's take a couple of minutes breather and then continue. For the next classes, we talked about histograms, and I just wanted to kind of give you a refresher about the different kinds of histograms we talked about, right? We talked about, there are really two kinds of histograms. There are what's called joint histograms and marginal histograms. So if you have a one-dimensional set of marginal things, then there is only one histogram to compute, right? So if you compute histogram of pixel intensities, it's a one-dimensional, 0 to 55. Or you have a histogram of visual words, so you have 100 visual words, so it's a 0 to 100, right? If you have a 2 or more dimensions, how do you histogram those? Let's say you have a color images. Those are RGB, so they're three-dimensional. How do you do histogram of color images? Well, there are a couple of ways you can do it. You can do what's called marginal histogram, which means you take every feature and then just do a linear histogram of each. So you have a red histogram, a green histogram, and a blue histogram. So now you have 3 arrays of histograms for each image instead of one. Okay? That's called marginal histograms. It's fine. It misses some information. What information does it miss? Correlations between those, exactly. And so to address that, you can also do joint histograms. A joint histograms is now, your histogram is not a vector, it's not a one-dimensional thing, but if you have two features, it's a two-dimensional thing. So it's a matrix or a tensor, right? So if you want to, for example, histogram x, y values, then you can do x separately and y separately, but then you're missing the correlations between the x's and the y's. So what you can do is you can bin your x, y space into squares and then histogram it in this way. Okay? Which ones are better?
Joint instrument.
Huh?
The joint one?
It's a trick question. So joint histograms are better at representing the information if,
We have lots of data.
if we have enough data. Exactly. If we have infinite data, this is the way to go. because that captures everything. The problem is that sometimes you don't have enough data, especially if you have 100 dimensions. So you have like 100-dimensional tensor. You really need a huge amount of data to fill it up with counts, right? So if you don't have enough data, it turns out that marginal histograms actually are better. Okay? Because then you don't have enough data to capture the correlations anyway. You know, you have barely enough to get something out. And so when you have little data, use marginal. If you have enough data, use joint. And they can also play with the size of the bins to adjust that as well. And so this kind of connects to a whole big thing about representation of different patches. We talked about representing patches as filter outputs, about just using raw patches. Another way of representing patches is what's called the SIF descriptor. And the SIF descriptor is kind of another way to histogram your filter responses. So here the idea is that you take a patch, you divide it into a 4x4 grid, and then you basically histogram the set of oriented filters that you computed within this each cell of the grid. So here it says, oh, here there is a lot of kind of edges going this way. Here there is a lot of edges going this way, right? So it's a kind of you have a little histogram at every grid, and then you also histogram the XY locations in a joint way, okay? So that's another way to take that V1-like information and turn it into a representation. And there has been a lot of other similar ways of doing this. So this is an example of 3 patches, and then it turns out that the SIF descriptor of all of these 3 patches is actually very similar to each other. It's almost identical. So it's kind of allows you some invariance, and so still said, okay, it's the same patch. There is also the hog descriptor that kind of does the same type of histogramming of different orientations, but on the scale of the full image. Slightly different, the different statistics. So you have, 8 orientations, 4 scales, 16 bins, etc., etc. So a lot of effort was done in coming up with these handcrafted descriptors to take the filter information from this kind of V1 representation and make it into a feature. People have also looked at making features kind of more foveated, have it dense at the center and sparse around. So one of them is called the shape context. So here is kind of a way to histogram. Here the histogram is not over XY location, but it's in the space of rho and theta. So it's a polar coordinate histogram. So you have your log r and theta, and you're basically the same kind of thing. You're counting your features in this kind of histogrammed way. There is another way of thinking about histograms, which is basically you just blur things. Blurring and histogramming turned out to be very similar things, because all what they're doing is they're giving you some invariance. So one way is you can histogram things, another you can just blur your signal, and that turns out to have the same thing. So here is a tool called geometric blur, which is essentially a soft, blurry version of the shape context. Instead of histogramming orientations, you just blur them. You can do the same thing on things like optical flows. So you can compute flow field in X and Y. You can separate them to make them only positive only, and then you can again blur them and use that as a representation. So there's a lot of representation that really all. There's another one called spatial pyramid matching. So I'm gonna just make sure you kind of you know all of these names, so when you see them in papers, you are not going to be completely confused. But I think the main story about them is that they're all ways of clustering and histogramming some underlying signal. Okay? So you have, they're all of these representations have the same kind of conceptual steps. You first compute some low-level features. For example, your oriented gradients in a kind of V1 representation. after you have computed those features, you somehow aggregate them together. So you do k-means on them, and then you can histogram them. Or you can pool them together, or you can compute means of them, or you can blur them, right? So you somehow you go from this infinitely many different filter vectors that will never repeat. You somehow compress that space in some way to get features that are more repeatable, okay? And then you use those features in your visual representation, and then you use some simple machine learning, nearest neighbor, linear classifier, whatever, to do whatever you want to do, okay? But the problem is that, you know, people have, as I showed, a gazillion different ways of using this kind of pipeline. Everyone has their preferred feature. Back in the 2000s, everybody had their own favorite feature. How do you know which are the best features? You know, and why do we think that somehow some person can decide, you know, what the right best feature is, right? So this was a question posed by one of our colleagues here, a professor in Berkeley, Bruno Altshausen, and his colleague David Field, who said, instead of trying to basically just blindly copy what V1 seems to be doing, can we somehow have an algorithm that figures out the best representation for our signal automatically? In any case, the thing is with V1, you know, we only know what is in V1. We don't even know what's in V2, right? So our knowledge is already kind of incomplete. So his question was how to figure out if we can come up with somehow optimal filters. Instead of saying, okay, we're just going to, you know, approximate these oriented Gaussians, derivatives of Gaussians. Can we come up with a set of filters from the data, a data-driven way? And this is probably one of the most famous papers in this space. It's a very, very important paper. I'm very highly recommend that you read this. I can just give you a very simple idea about this. Basically, the idea is they decided to say, if my goal is to represent visual imagery, if I know that my signal is natural images, right? Not some random patterns of ones and zeros, but natural images, right? So images that live on the natural manifold, right? So we talked about how, you know, a 10 by 10 patch of an image has, you know, there are more 10 by 10 patches than atoms in the universe, right? But actually a very small slither of that is actually ever going to exist in the real world. Most of those random things are just going to look like random stuff, and nobody's going to think that they are natural images. So there's actually a very small subset of those possible images that could actually exist. And so Bruno's question was, can we find the optimal representation for the type of data that we see every day in our world? So what they did is they took, you know, 1,000 images or 10,000 images out from, you know, Flickr or whatever, online somewhere, real photographs. And they said, what would be the best representation? If I were the brain, if I was evolution, what would be my best representation of the natural world? Remember how we talked about, you know, why human vision is sensitive? The visual part of the electromagnetic spectrum, the visible light, is, you know, 440 to 770 nanometers, because that's ecologically that's what the sun has been giving us. And so we adapted to the sun. They said the same kind of argument. They said, if the natural world gives me natural images that have this kind of structure, what would be the best way to model, to represent that natural world? Make sense, the setting? Yes? Well, it doesn't quite make sense to me, because this is all nice and good, but how do you measure what is good? A goodness of the representation. It's also not clear how to measure it. So they came up with a measure that, it's one of many, but it's as good as any, really. The idea is that they're going to try to represent each patch as a linear combination of a set of filters. So we know that V1 has these filters, right? We know that they're like things like oriented, simple, complex edges, whatever. We're going to forget about what they know about what's in the filter, but we're going to say, okay, there's a whole bunch of filters, and you apply a whole bunch of filters to an image, and then you use that to represent the information. Okay? So basically what we're going to do is we're going to say, I'm going to look at the error between my image patch and a best reconstruction of that image patch using a weighted sum of your k basis patches, basis vectors that you have, like the filter bank, for example, right? So you have alpha times this basis set phi. And I'm going to say, I'm going to look at the best way to represent every patch, and then I'm going to sum over all the patches, and I'm going to minimize that. Okay? So I want to have the best representation to preserve the information about the image. So a best way to kind of model the image with a set of k basis patches, k filters. So far, so good? Well, they also added another assumption. They say, on top of that, because if you just do that, what does this look like? This looks like something you've seen before. You have a set of bases, and you want the best representation given those bases.
PCA.
It's PCA, right? And we know that PCA is not that exciting. And we know that those PCA bases, they don't really, they're too generic. They try to model the average representation for everything. So they didn't want PCA. And then they said, oh, what is another constraint that we can add to this? And then they realized that another constraint is that it seems like, at least though both these people are neuroscientists, so they actually have done some experiments on looking at the neurons in the brain, and they say that it seems like it's very rare that you have all the basis filters participating on a particular patch, in a particular visual field. Usually you have only a few active cells firing. So you have a couple of cells firing, and all the others are staying silent. So what does that mean? It means sparsity. It means that in this representation, the alpha vector is sparse. It's not like it has like 0.1 of everything. No, a few things are close to 1, and everybody else is 0. Okay? So what they did is they said, okay, I want this alphas to be sparse. I want the vector of coefficients to be a sparse one. Okay? So now it's basically you have PCA plus sparseness. So it's not a very complicated thing. It was actually a very simple paper. So let's see how well can we do. And then the question is, of course, to find out what those filters are. To find filters that would behave in such a way. Okay? And the reason that the paper made such a splash and was so big was that you code up this very simple criterion, this very simple constraint. You want to, represent the data, and you want the representation to be sparse. Only two things. And then, are you ready for the results? Ta-da! These are the set of filters that was the result of that optimization. Now, that should strike you as something very peculiar immediately, and maybe they'll see why this was so exciting when the paper came out. What's peculiar about this? What does this remind you of? It looks not that different from the oriented filters that Hubel and Wiesel found in V1 all those years ago. But here, we did not put in any of that information inside of the optimization. We did not say, I want to have gradients. We didn't say, I want to have simple edges. We didn't say, I want complex edges. Right? We didn't say anything. We just say, start with random patches and then just optimize for things that would satisfy that equation. And yet, given that we ran it on natural images, this is what it came out with. Now, if we ran it on just random images, or images of some other planet, or I don't know, just something else, like medical images, it could be that these things will be completely different. So if you have random images, it will definitely be different. So it seems like this pattern, at least the kind of the V1 type filters, are in a sense an evolutionary response, an evolutionary adaptation to the type of data, the type of visual information that we are seeing. That this somehow seems to be the right representation for the kind of visual data that we are seeing. So that was why this paper was so exciting. Let it sink in for a bit. Question? Yeah?
So if we just have the PCA component, what are the kind of filters that are learned?
So if you have PCA, you basically get something that is like, it's not that different from Fourier basis. So you have, essentially, you have sine waves of different scales. Yeah. Yeah?
So if they only uses like linear combinations of like filter responses, the reconstruction results will probably not be that good, right?
They're not great, but they are okay. Remember that these are, the reconstructions are on these, I think they use like 7x7 or 9x9 patches. So it's not like you're representing the entire image with one filter, right? You're still doing it per patch. So you only need to reconstruct that patch. So I think the reconstruction results weren't that bad. I mean, they weren't like photorealistic. It wasn't like, you would be able to tell the difference between the real image and the reconstruction, yes. But, there would be some noise, but it wasn't a huge error. It was actually reasonably good at the reconstruction. Yeah. Stella?
Clarification following this question. For sparse coding, you need more bases. So it's called over-complete bases. Compared to PCA, you need, say, 100. We know that, say, 100 PCAs should be sufficient to representing the signal. But if you go for sparse coding, you need a whole lot more, 500 something.
Right. And in fact, all of the stuff we have talked about, the filter bank representations, all of them are all over complete, right? So these 40 filters in the filter bank we had, you don't need 40. You actually, you need much less if you just want to represent the signal. So, and here again, they actually computed, they computed like hundreds, I think maybe 200 they had of this in the dictionary here. So again, it's much more than you actually need if you just want to kind of compress the signal.
Yeah, if it's 7x7, at most you need 49, right? The dimensionality is 49, right? PCA full, PCA base is only 49, but here there's a lot more than 49.
Yeah, yeah. But the same thing like in V1, right? You only need, derivative in X and derivative in Y to get all the other things, right? But yet they have different orientations. You technically don't need them, but the brain has them because it's an overcomplete representation, yeah. And that's kind of another reason for why this sparsity thing is there, because then once you have an overcomplete representation, you can afford to be sparse. And then why sparsity is there, I think there is some argument on that. Basically it's cheaper, right? If you don't have everything going on at once, that it's cheaper energy-wise. You don't need to send all of these wires. You don't need all the neurons to be active at all the time. You have some neurons that are resting. So I think there is some energy and explanations of why sparsity is good. But there is also a representational reason as well. Yeah? Okay, yeah?
So in the equation, so there's some kernel defined here?
No, it's not a kernel. It's just this is just that's their basis. This is their model for the basis patch.
Yeah, I'm wondering whether they predefined some structure for that. So that's why they got to the following.
No, that's the magic. They didn't predefine anything.
Okay, even for that.
Nothing. No, this is just an empty patch. Empty patch. I think they initialize it with random noise, I think. No, that's the beauty of it. No, nothing. The only thing they put in, the only piece of kind of human knowledge, is the sparsity prior. This sparsity prior right here. That you can argue, well, that's you know something about the human brain, so you put it in, right? Everything else just comes out of the data, and that's what makes it so exciting. So now, next time you see Bruno on campus, you can say, "Oh, you're amazing! I saw your amazing paper." Okay, but it was really amazing. I when I saw it, I was like, "Wow!" Okay, and in a sense, so that's basically what we have. What we have so far is we knew that the neurons get more and more specific to a particular visual pattern as we go farther and farther, right? You start with neurons that are basically like photoreceptors, then you go to neurons that are spots, then you go to neurons that are simple cells oriented, then to complex cells oriented with shift invariants. As higher you go, they get more sparse and more specified, right? So we have learned that. Hubel and Wiesel told us that as you go to V1, that specificity is in the orientation space. That you can model that with a convolution. The convolution provides a pretty good model for this story, and that we have also seen that with this very simple kind of a feed-forward mechanism, we could actually model a lot of seemingly complex behavior. We can model things like pre-attentive recognition of images. And we also saw that we could actually get at what those filters look like directly from the data, directly from the signal. Okay? And this is kind of where the neural networks come in. Right? Because these were the conditions that said, aha, we have learned so much from, thank you, Yulish. Thank you, the folks that did the Hubel and Wiesel. Thank you, Bruno Althausen. All of that information suggested that maybe we can somehow try to now model this hierarchy. Okay? Because if you look at what all the methods that we have seen and all the papers that we have seen so far, they suggested that there is this hierarchical structure. But they haven't gone past V1. So we know what's in the retina, we know what's in V1, what's in V2 and later on, actually even now we don't know. And back in the 80s, people really had no idea what's farther on. But we do know that there is this hierarchical layer. And so this is where the neural networks come in, and the neural networks, probably the key paper in neural networks is this work in 1980 by Fukushima. Okay? And it's a remarkable paper because a lot of the things that you think are kind of modern, newfangled stuff, it was all in this paper. Okay? Like, what is the big thing? Why can we now train deep networks as opposed to the 80s? Does anyone know? Computational power data is definitely the most important things, but there was also one algorithmic reason. Huh?
Backpropagation?
No. Well, backpropagation was known, in the 30s. The nonlinearity, right? We'll talk about this later, but turns out that the nonlinearity that everybody is using now, it was in the Fukushima paper. The max of 0 and x was actually in the original paper. So the Fukushima basically said, I want to take the ideas from Hubel and Wiesel, the hierarchical structure, and this idea of basically looking at computing new features as combinations of previous features and just going forward. And I'm just going to try to make a computational model of it. Okay? And that's basically what he did. And so he actually called them. He said, okay, I'm going to have my retina, LGN, I have my simple cells, I have my complex cells. How do you go from simple cells to complex cells? That's max pooling, right? You're going to be pooling over the simple cells to get complex cells. And then you say, okay, now I'm going to have a hyper-complex, higher complex, and then he kind of ran out of names. But basically, he was doing exactly, just copying exactly what Hubel and Wiesel kind of suggested they thought was happening in V2, V4, and etc. Even though there was no evidence of that at all. Okay, so the Fukushima paper was probably still is the most important paper. The only thing it didn't have is it didn't have backprop. What it did instead was a type of unsupervised training that is kind of, you can think of it as kind of a hierarchical version of k-means. Okay? But we'll find later that this still works pretty damn well. Okay? But this is probably the first paper. And then, of course, Jan LeCun comes on the scene in really late 80s. Inspired by the Fukushima work, and says, okay, but now let's say if I want to actually have this. So the Fukushima work was unsupervised. It was basically just a mechanism for going from pixels to some higher order features. It didn't have a task. And Jan is also always a kind of a very practical man. He was always into doing something that works. And he said, okay, I need to recognize zip codes on post office wants me to recognize zip codes really fast. What do I do? Well, I need to have a classifier that recognizes digits. That's where the MNIST digit data set comes in, right? You have 10 digits, you want to recognize them, you have to do it really fast, and you have a task. So in the end, you don't just want a representation. You actually want to have something that basically in the end says, okay, I have a vector of 10 values and then tell me one of the 10 digits. Okay? So then He said, okay, to do that, I want to do backpropagation. I want to basically find out, and we'll talk a little bit more about that, I want to go, what are the weights? What are the parameters? What are the filters, you can think, that I need to set up such that, given a new image, I classify it into one of 10 digits. Okay? And that the method of setting those filters, those weights, is backpropagation. But the amazing thing, and this is where I'm going to end for today, the amazing thing that happened, and this kind of hopefully ties it all together for you guys, is that as you set up this supervised pipeline where you say, okay, I'm starting with an input image, and I'm going to end up with some sort of a classifier that says either digits, or in the case of natural images, I want to have classes maybe of cars and trucks and whatever, faces and whatever not. As I train this pipeline, once it's trained, I can then look back and I can look at least at the early features. I can look at the first layer features, for example. And the first layer features, they're the same thing. They're little patches. There are patches applied to the image. So they're just filters. And I can look at those filters, and I can visualize them. And what do they look like? They again look like your V1 filters. Again, we started from nothing. We didn't put in any knowledge about the structure of the visual cortex, except for this idea of hierarchical structure. That was the only assumption that we have here. We didn't here even need to do sparsity. So Bruno needed to do sparsity. Here, we just have hierarchability. And again, we get stuff that looks like V1 neurons. But what's more is that we actually can go farther, and we can say what happens at the next layer. And you can see that you get features that are a little bit more complex. And then you go to another layer, and you have it even more complex. And so this is how everything ties in together. We started with the first impetus was Hubel and Wiesel figured out what was in V1, told it to the world. Everybody got excited. Jülich started modeling the idea of textons and how do you represent visual world with some sort of a dictionary of some visual elements. Bruno Altshausen came up and said, okay, how can we come up with a representation that, given natural images, can have a dictionary that actually ends up modeling the visual cortex. And then Fukushima said, let's just model the whole thing, not just the piece we know, but let's just go model the whole thing. And then Jan LeCun came and said, okay, this whole big model, it's nice, but it's not really being useful for anything. So let's make it useful by having a task at the end, and then use backpropagation to train for that task. And as you do that, you again arrive with something that goes back to biology and says, oh, wow. We are getting something where something is emerging in the data that looks very similar that what looks like is happening in our visual cortex. And that's kind of exciting. And this is why, this is part of the reason why neural networks have been such an exciting thing, because it seems like not only are they working well for problems where we have done a lot of hand coding, but they also seem to give us a representation that has some similarities to the one up here. There's of course many differences, and nobody's claiming that this neural network is any in any way exact equivalent of what's happening here. But there is enough interesting parallels that this is actually also interesting, not just for applied computer vision, but also for people studying studying neuroscience, and people have. Any questions? Okay, so Wednesday we're going to discuss ConvNets, and presumably the next piece of the homework is going to be then you'll be able to be ready for that. Okay? See you on Wednesday.
So when you first showed the tubular meso video,
Mhm.
there was this like neuron